In most scenarios, a transformer isn't essential for stepping down voltage within a motor starter's control circuit. Typically, the control circuit operates independently from the power circuit, and the coil voltage is predetermined by the starter's manufacturer. In this specific instance, an Allen-Bradley size 0 starter is designed for a 120 volts coil, making the neutral wire acceptable for the neutral return. However, certain situations warrant the use of a control circuit transformer. Firstly, when dealing with a starter powered by voltages exceeding 240 volts, a transformer can step down the voltage to a safer level for the control circuit. Secondly, a transformer provides isolation between the control circuit and the power circuit, which is advantageous in environments with electrical noise or transients. Thirdly, a transformer with isolated secondary windings can provide ground fault protection for the control circuit. In your setup, because the starter is rated for 120 volts and the control circuit is isolated, a transformer is not needed. Regarding fusing the control wiring, it is generally not required unless there is a risk of a short circuit or overload. In your case, the control wiring solely powers the coil, typically a low current device. Given the installation of 10 amps fuses upstream of the starter, overloading the control wiring is unlikely. In summary, based on the information, it is not necessary to use a transformer for the control circuit or to fuse the control wiring. The installation appears safe and functional. Let's delve deeper into understanding motor control circuits and the role of transformers. A motor control circuit is the portion of an electrical system that governs the starting, stopping, and protection of an electric motor. It's the brain behind the operation, ensuring the motor functions correctly and safely. A motor starter is a device that provides overload protection to an electric motor, as well as starting and stopping capabilities. It typically consists of a contactor and an overload relay. The contactor is an electrically controlled switch used to turn the motor on and off. The overload relay protects the motor from excessive current draw, which can cause overheating and damage. The control circuit uses low voltage, often 120 volts, to operate the coil of the contactor, which then closes the main power contacts to supply the higher voltage, such as 208 volts or 480 volts, to the motor. Now let's consider the use of a control transformer. A control transformer steps down the higher voltage of the main power circuit to a lower voltage, typically 120 volts, for use in the control circuit. While not always necessary, it offers several advantages. Firstly, safety. Using a lower voltage in the control circuit reduces the risk of electric shock to personnel working on the equipment. Secondly, isolation. A transformer isolates the control circuit from the power circuit, which can help prevent electrical noise and transients from interfering with the control circuit's operation. Thirdly, standardization. In facilities with multiple motors and starters, using a standard control voltage, such as 120 volts, simplifies wiring and maintenance. Now let's talk about fusing the control wiring. Fuses are overcurrent protection devices designed to protect electrical circuits and equipment from damage caused by excessive current. In the control circuit, fuses are typically used to protect the control transformer, the control wiring, and the coil of the contactor. The size of the fuse should be selected based on the ampacity of the wiring and the current draw of the components it protects. Overfusing can defeat the purpose of the fuse itself. The NEC National Electrical Code provides guidance on fuse sizing and wiring protection. Several factors determine whether you need a control transformer. The voltage of the power circuit is important. If the motor operates on a high voltage, such as 480 volts, it's common to use a control transformer to step down the voltage to 120 volts for the control circuit. The control circuit voltage requirements need to be considered. If the starter's coil and other control components are designed to operate on a specific voltage, such as 120 volts, you need to provide the voltage to the control circuit. The presence of electrical noise or transients is another factor. In environments with a lot of electrical noise, a control transformer can help isolate the control circuit and prevent interference. The facility standards and preferences are also important. Some facilities have standardized on using control transformers for all motor starters, regardless of the voltage level. In your specific situation, you have a 1.5 horsepower, 3-phase, 208 volts motor connected to an Allen Bradley size 0 starter with a 120 volts coil. You've used the neutral wire for the control circuit return. Given these parameters, a control transformer is not strictly necessary. The 120 volts coil can be powered directly from the 208 volts line to neutral. However, it's crucial to ensure that the neutral wire is properly sized and grounded to handle the control circuit current. Whether or not to fuse the control wiring depends on several factors. The primary consideration is the risk of a short circuit or overload. If the control wiring is properly sized and installed, and the coil is the only load in the circuit, the risk of a short circuit or overload is low. However, if there is a possibility of damage to the wiring or if other loads are connected to the control circuit, fusing is recommended. According to the NEC, control circuit should be protected against overcurrent. Section 430.72. B specifically addresses overcurrent protection for control circuits. It states that control circuit conductors must be protected against overcurrent in accordance with their ampacities. There are exceptions, such as when the control circuit is supplied by a Class II transformer or when a control circuit is integral to the motor starter. However, in general, fusing is a good practice to ensure the safety of the control circuit. In your case, since you are using a 120 volts control circuit and the only load is the coil, a small fuse, such as a 1 amp or 2 amp fuse, would provide adequate protection. The fuse should be installed in the ungrounded conductor of the control circuit close to the point where the circuit is tapped from the power source. Let's discuss the potential advantages and disadvantages of using a control transformer in your setup. One advantage is increased safety. Using a control transformer isolates the control circuit from the 208 volts power circuit, reducing the risk of electric shock. Another advantage is improved noise immunity. A transformer can filter out electrical noise and transients, which can improve the reliability of the control circuit. A third advantage is easier troubleshooting. With a separate control transformer, it's easier to isolate and troubleshoot problems in the control circuit. However, there are also some disadvantages to using a control transformer. Firstly, cost. A transformer adds to the overall cost of the installation. Secondly, space. A transformer takes up additional space in the control panel. Thirdly, complexity. A transformer adds to the complexity of the control circuit, which can make it more difficult to troubleshoot. Here are some additional considerations for your industrial mixer installation. Firstly, ensure that all wiring is properly sized and installed in accordance with the NEC. Secondly, use appropriate strain relief for all wiring connections to prevent damage from vibration or movement. Thirdly, label all wiring and components clearly for easy identification and troubleshooting. Fourthly, perform regular maintenance on the motor starter and control circuit to ensure proper operation. Fifthly, follow all safety procedures when working on electrical equipment, including lockout/tagout procedures. In conclusion, while a control transformer is not strictly necessary in your specific situation, it can offer several advantages, such as increased safety, improved noise immunity, and easier troubleshooting. Using the control wiring is generally recommended to protect against overcurrent and short circuits. Always consult the NEC and other applicable standards for guidance on electrical installations. Let's consider the potential fault scenarios and how fusing can protect the control circuit. If the coil of the starter were to short internally, it would draw excessive current. Without a fuse in the control circuit, this could potentially damage the control wiring, the limit switches, and even the upstream power source. The 10 amps fuses upstream of the starter are intended to protect the motor and the main power circuit, not necessarily the control circuit. Therefore, a smaller fuse in the control circuit would provide a more targeted protection for the control wiring and components. If a wire in the control circuit were to become damaged and short to ground, a fuse would quickly interrupt the circuit and prevent further damage. Without a fuse, the short circuit could create a fire hazard or damage other equipment. In addition to fusing, it's also important to use proper wiring methods and materials. Use appropriately sized conductors for the control circuit wiring. The NEC provides tables for determining the ampacity of conductors based on their size and insulation type. Use conductors with the appropriate insulation rating for the voltage and temperature of the control circuit. Ensure that all wiring connections are tight and secure. Loose connections can create heat and lead to electrical problems. Protect the control wiring from physical damage. Use conduit or other protective measures to prevent the wiring from being cut, crushed, or otherwise damaged. Ground the control circuit properly. Grounding helps to prevent electric shock and provides a path for fault current to flow back to the source. Regularly inspect the control circuit for signs of damage or deterioration. Look for frayed wires, loose connections, and other potential problems. Address any problems promptly to prevent them from escalating into more serious issues. If you are not comfortable working on electrical equipment, consult a qualified electrician. Electrical work can be dangerous, and it's important to have the knowledge and skills to do the job safely. In summary, fusing the control wiring is a relatively inexpensive way to add an extra layer of protection to your industrial mixer installation. While it may not be strictly required in your specific situation, it's a good practice to ensure the safety and reliability of the control circuit. Remember to follow all applicable codes and standards and consult a qualified electrician if you have any questions. Consider the following example. Suppose a wire in the control circuit becomes pinched between a metal enclosure and a sharp edge. Over time, the insulation wears away and the wire shorts to ground. Without a fuse, the full available fault current flows through the wire, causing it to overheat and potentially start a fire. With a fuse, the fuse blows quickly, interrupting the circuit and preventing a fire. The cost of the fuse is minimal compared to the potential damage that could result from a fire. Let's also discuss the types of fuses that are suitable for control circuits. One common type of fuse is the Class CC fuse. Class CC fuses are compact, current-limiting fuses that are designed for control circuit protection. They have a high interrupting rating, which means they can safely interrupt high fault currents. Another type of fuse is the midget fuse. Midget fuses are small and expensive fuses that are commonly used in low-voltage control circuits. They have a lower interrupting rating than Class CC fuses, but they are still adequate for many control circuit applications. The type of fuse you choose will depend on the specific requirements of your control circuit. Consult the fuse manufacturer's specifications to ensure that the fuse is suitable for your application. When selecting a fuse, it's important to consider the following factors. Firstly, the voltage rating. The fuse must have a voltage rating that is equal to or greater than the voltage of the control circuit. Secondly, the current rating. The fuse must have a current rating that is appropriate for the ampacity of the control wiring and the current draw of the components it protects. Thirdly, the interrupting rating. The fuse must have an interrupting rating that is high enough to safely interrupt the maximum fault current that could occur in the control circuit. Fourthly, the time delay characteristics. The fuse must have time delay characteristics that are appropriate for the application. Some fuses are designed to trip quickly, while others are designed to allow temporary overloads to pass without tripping. Remember, safety is paramount when working with electrical equipment. Always follow safe work practices and consult a qualified electrician if you have any doubts.